Okay, so good afternoon, everybody. I would like to thank the organizers for this conference and also for inviting me. So my name is Maayan, and I will present a talk that discusses age-related navigational declines and also ways to support wayfinding in aging. Now, in this talk, I will present studies that use virtual reality as an experimental method to explore wayfinding in young and older adults. So let's talk about navigation. How do we navigate? How do we know where we are? So in order to navigate, we can rely on two types of spatial reference frames, or you can say two types of navigational strategies. One is the egocentric strategy. In this one, we code locations relatively to our own position. For example, you can see that the person in the image can code a specific distance and direction from himself to the window. By that, he can establish a path, a route from his position to the target, and replicate it later when you reach this location again. So, route learning supports egocentric navigation. On the other hand, we have the allocentric spatial reference frame, or allocentric navigational strategy. In this one, we code locations relatively to other landmarks in the environments. For example, the person can code that the location of the window is in a specific distance and angle from the chair and another distance and angle from the books. So here it doesn't matter where he stands because the relations between the locations is fixed. So this one is landmarks-based navigation. So he can remember the location of the window relatively to other landmarks in the environments. And apparently, different brain networks support different navigational strategies. And the allocentric reference frame is supported by areas that are in the medial temporal lobe, you see here in red, including the hippocampus, while the egocentric spatial reference frame is supported by other brain areas as the parietal cortex and other areas that support stimulus response. Now, when looking at age-related navigational declines, you can see that one of the first areas that show age-related neurodegeneration, and even in normal aging, like in here, so one of the first areas overlaps the areas that support navigation, specifically landmarks-based navigation, the allocentric network. And indeed, many studies show that older adults show selective deficit in landmarks-based navigation, but not in route learning navigation. And the next slides will demonstrate this effect. So the first study is a study from the Moffat Lab, Scott Moffat Lab, and was published in 2012. Here, it was a translation of method from rodents to humans using virtual reality, and people learned that a specific target, okay? They entered this arm of the maze, of the Y maze, and go straight and then took the right turn, and the location or the target location was near the landmarks of the heart in this example. Later, at the probe trial, participants entered without knowing from a different arm of the maze, and they could use two different strategies. They could either replicate the route by going straight and take the right path, and this is an egocentric response, or replicating the target by associating it to the location of the landmarks, and this is the allocentric probe response. Now, when looking at the strategies that young and older adults used, the y-axis is the number of participants. You can see no specific preference of strategy in the young group for one strategy. However, older adults specifically preferred the egocentric strategy over the allocentric strategy. Now, in this experiment, this is a study that I published in 2019. I used virtual reality in order to dissociate each navigational strategy. This is something that we can only do in experimental setup, but not in real life, because it is hard to have a situation without landmarks, and also it is hard to avoid generating path learning. So what did I do? In the ecocentric condition, there are no landmarks in the environments. Okay, only endless gray plane. And participants learned a specific route from a starting position to a target, for instance, the plant or the umbrella. And the same path was replicated along the learning trials and also later at the retrieval trial, so people could learn a route. It was route learning, pure route learning. On the other hand, in the allocentric condition, there were landmarks in the environment, so people could tell that the plant is near this instrument, while the umbrella is near this building. On the other hand, there was no consistent route because during the learning trials and also later at retrieval trials, participants approached it each time from a different position. So this was the way to isolate the allocentric, landmarks-based learning. And you can see that in the egocentric condition, there was no difference between young and older adults when looking at mean distance errors when people had to retrieve the locations of the objects. However, in the allocentric condition, there was a selective deficit, navigational deficit in older adults that show longer distance errors compared to young adults. This is another study that was published last year. Here we show that when the spatial cue reliability is higher, navigational performance is better. And we use two types of spatial cues. One is landmarks, and the other one is optic flow that represents self-motion, like route learning. And we had two reliability levels for the optic flow and for the landmarks. The capital letters represent the higher reliability and the non-capital letters represent the low reliability. And we had a combination of both two reliabilities for each spatial cue. Eventually, we had 4 conditions. And we see tested how young and older adults navigated in each condition, in each one of the 4 conditions. And we measured the accuracy and precision of their performance. It was a homing task. And we found that indeed a higher reliability of both spatial cues improved navigational performance. However, older adults were less sensitive to changes in landmarks reliability. So altogether, older adults rely less on cues like landmarks, okay, but use route learning as well as young adults. And when they have the ability to choose the strategies, they will prefer the route learning strategy over the landmarks-based strategy. Now, apparently, age-related navigational declines is one of the sources for reduced mobility in older adults. And this reduced mobility can lead to unpleasant situations as social exclusion and also dependent lifestyle. Now, in the next slides, I will present a collaboration between architecture and cognitive neuroscience. And the goal of this collaboration was to design guidelines that support wayfinding in aging. Apparently, most of the attempts to improve wayfinding so far mainly focused on landmarks navigation by adding more landmarks or stronger landmarks to the environment. But in this study, we wanted to test if wayfinding can improve by strengthening route learning strategies. And we assumed that it should be easier to form and then later to retrace an association between a route and a target if each target is accessed by a specific path. Accordingly, we hypothesized that a star-shaped design of pathway will make it easier to generate a selective target route association. You can see here that there is only one way to get to this target and one way for this target as well and to this target. However, in the grid-shaped design, there are many ways that you can take from the start point to the target, okay? So you cannot associate it with a specific path. So in order to test these assumptions, we first used a navigational task on a desktop, and we had a group of young adults and group of older adults, and participants navigated either in a grid design or star design of the same identical environment. And the only difference between the two environments that in the star design we added additional 5 transparent walls. They were transparent, so there was no difference in visibility between the two conditions. But you can see that by adding those walls, we transformed the grid design into a star design, and with the center and arms that reach out from the star, from the center. And in the star design, there is only one path that you can take in order to get to each target shop in this shopping center, while in the grid design, you can get to the same shop from many directions. So it is harder to associate specific target with a specific path. And we found that when looking at blind retrieval, so people have to retrieve locations according to their memory and navigate to the location of each shop, there was a selective effect of design with shorter distance arrows in the star design, suggesting that there is superior navigation in the star design when looking at distance arrows. You can see that older adults demonstrate longer distance arrows, which is in line with the literature about what we know about age-related navigational declines. However, there was no age on design interaction, so the effect was not selective for older adults and was the same for both age groups. Later, we wanted to see what happens when we let people navigate in real-life conditions. And accordingly, we used immersive virtual reality with a large-scale motion tracking system. And we created another layout that fit the physical dimensions of the space. And again, we transformed the grid design into star design by adding 1, 2, 3, 4 transparent walls to the environment. So now there is only one way to get to each target shop, unlike in the grid design that you can access each target shop from many directions. And we assume that it will be easier to remember this route learning in the star design. So you can see a demonstration of what people see when they visit the virtual reality and walk in it. Okay, this is one of the versions of the environment that we had. And this is a young participant performing the task in virtual reality, navigating in the shopping center. You can see also that older adults perform this task, not only young adults, and they do it well. Okay, and as before, as in the desktop task, we found that there was a superior effect of wayfinding in the star design with shorter distance arrows with better navigational performance. Again, older adults in general showed longer distance arrows, and we didn't find a selective effect of age in the star design. So it was beneficial for both age groups. So to conclude, I presented some navigational studies using VR in young and older adults. And unlike landmarks-based navigation, route learning is relatively preserved in aging, and older adults tend to over-rely on route learning strategies. I showed you that pathways design can enhance route learning and result in superior navigational performance. However, this effect was not selective for older adults. It was found in the same manner in both age groups. And I would like to thank first Professor Thomas Roberts from the German Center for Neurodegenerative Diseases. Two of the first studies that I showed you at the beginning of the talk were performed in his laboratory, and also to Professor Daphne Fischer-Gewirtzman, who is also from the Faculty of Architecture at the Technion, where we tested the comparison between grid and star designs in her laboratory.